So we continue with the second page. Has to do with Taylor series and Maclaurin series. And so these are formulas that you need to know. I've gone ahead and done some things here, but I'm just going to point out what you need to know. You see the formula right here is the Taylor series for a function which has derivative values evaluated at the point A. So when you expand a function in a Taylor series, you have to expand it about some point A. So the first thing I did was take 5 derivatives because we want the 5th degree polynomial. And I've evaluated each of those derivative values at pi by 4, A equals pi by 4. And then I have put it into this formula here, as you can see. And when I do that, you can see the function values here put in. For instance, here's f at pi by 4, and here's f primed at pi by 4, and so on, f second derivative at pi by 4. And then we have x minus a squared for the second order term, and so on. So there it is. That is what you need to be able to do. You need to be able to remember the formula. You need to understand that you evaluate the derivative at some point, the point you're expanding about, a equals pi by 4. Okay, so now let's move on and look at the next problem. It's a Maclaurin series. When we say Maclaurin series, we mean the Taylor series where a is equal to 0. So we have our function. I have taken all kinds of derivatives here up to the 5th order. I've done that, so I'm going to see the pattern. We're doing an infinite Maclaurin series here. The previous problem was the 5th Taylor polynomial, so it stopped after the 5th order term. But the derivatives I've taken that many, just so I'm going to see the pattern that's there. And so now we have the function values at 0. There they are. And you'll notice that I have not written out, I have not multiplied that out. I leave that in expanded form because that is going to allow us to see some cancellations that we will have later on. So here's the f of 0 term, it's 0. See, up here we have 0. And the squared, the first order term, the second order term, and I put in the function values, and you see how these factorials cancel. For instance, here's 2 times 3. That's, if we'd written that out as 6, we might have missed the pattern how that's going to continue on. Notice here's 2 times 3 times 4 over 5 factorial. It's really 4 factorial over 5 factorial, which is 1 over 5. So there we have it. And so by the time I substitute in, we have this. It's a polynomial. It's a powers of x. And here it is when we look at the summation in summation form. You will notice that I have minus 1 to the n plus 1. That is because for n to an odd power, it's positive. And for n to an even power, it is negative. And so that means minus 1 to the n plus 1 accomplishes that. Finally, we look at the ratios, find the radius of convergence. And again, just like on the previous page, we did the ratio test. Putting it in, we get that, and we get that. And you'll notice at this point that the part that's right here, n over n plus 1, that goes to 1. Okay, divide top and bottom by n, for instance, which accomplishes that. And so we get that the radius of convergence is 1. If we were to do the endpoints, didn't ask for that, didn't ask for the interval here, but if it did ask for the interval, we'd be writing right down right now, -1 less than x less than 1. And then we're wondering about the endpoints. And I'll do one of them. Let's do x equal to 1, just to see what we get, just like on the previous page. I put that back into our summation, which is right here. And so we have summation n equals 1 to infinity. And we have -1 to the n plus 1 over, so the x is equal to 1 over just n. Notice what that is. That is convergent. Why? That is the alternating harmonic series. And you can assume, you can say that that is 1 if you like. That satisfies the test for alternating series. But we can just, when we notice the harmonic series, 1 over n, alternating because -1 to the n plus 1, and that is convergent. You may assume that. When you try x equal to -1, you will see that you get divergent because you will get just the harmonic series. So you should try to do that, see how that works out for you. And so the interval would be -1 less than or equal to, excuse me, just less than x less than or equal to 1 for the interval of convergence. So we'll stop here.